Swayam Prabha. Digital India. Educated India.
Hello students, welcome back to this BSc Semester 1 Chemistry Honours course of our curriculum, in which we are discussing about various properties of atoms which are called as the periodic properties. In this second module, lecture 4, we will be discussing about some typical questions based on the periodic properties of the atoms. This is Professor Ravin Zugade from Department of Chemistry, Rashtrasant Tukadoji Maharaj, Nagpur University, and this lecture has been prepared under the academic expertise of Professor L.J. Paliwal. Start with the first question. Why cation is smaller in size while anion is larger in size as compared to a neutral atom? Now we know that the cation is formed by loss of electron, and when an electron is lost, what happens? The nuclear force experienced per electron increases because the number of nucleons or number of protons in the nucleus, they remain same. As a result, nuclear charge remains same while one electron is lost. As a result, what you get is the nuclear force per electron gets increased. Hence, the ionic radius decreases due to greater force of attraction experienced by the electrons towards the nucleus. So they get shifted closer to the nucleus and ionic radius decreases. On the other hand, anion is formed by gain of electron, and since an extra electron is added, the nuclear force experienced per electron gets decreased, and hence the ionic radius increases. As a result, what we have is the cation is smaller in size while anion is larger in size as compared to a neutral atom. Why atomic radius of noble gas element is generally larger than previous halogen atom? Now we know that noble gas elements are present on extreme right corner of the periodic table, while halogens are just previous to them. So as we know that the atomic radius goes on decreasing across the period, hence it is expected that noble gas atom should have smaller atomic radius as compared to the previous halogen atom. Quite obviously, since the atomic radius goes on decreasing from left to right, and halogens are present on left hand side while noble gas elements are on right hand side. However, we know that noble gas does not undergo bonding, so these elements remain as monoatomic gases, and hence the radius which we consider in case of noble gases is the van der Waals radius, and in van der Waals radius the atoms are not close packed, but they are slightly away from each other, and halogens are forming a covalent bond, and hence in halogens the atomic radius is nothing but the covalent radius obtained from the X2 molecules like Br2, Cl2, F2, I2, etc. Now whenever covalent bond is formed, the atoms are overlapping on each other, and as a result the covalent radius is always smaller than the van der Waals radius. Hence, as a result, what we get is the atomic radius of noble gas is generally larger than the previous halogen, even if it is expected that since it is the next element as compared to halogen, it is expected that its atomic radius should decrease, but it increases since it is considered as the van der Waals radius as an atomic radius. Why effective nuclear charge is much smaller as compared to actual nuclear charge? We know what is the actual nuclear charge is equal to the number of protons which are present in the nucleus, or the actual nuclear charge is nothing but the atomic number Z of the nucleus. Now, this nuclear charge experienced by the atom, by the electron which is present in the shell or subshell in an atom, that is called as the effective nuclear charge. Now, actual nuclear charge depend on number of protons, or what we call as atomic number. Now, each electron in an atom is at different distance from the nucleus. So, first shell electron is closer to the nucleus, second shell electron is away from it, third shell electron is further away, and so on. Now, due to intervening electrons, there is a reduction in the force of attraction between the nucleus and outer electrons. There are two aspects to this. We know that the force of attraction between two charges is inversely proportional to distance between them. So as the distance goes on increasing, the force of attraction goes on decreasing. And secondly, the intervening electrons, it means that if we are considering valence shell, suppose the valence shell is a third shell, then the electrons which are present in first and second shell, they are called as the intervening electrons, or the electrons which are present in between the nucleus and the outermost electron. Hence, what these intervening electrons do, they act as a shield from the nuclear force. This leads to what is called as a shielding effect, and this shielding effect reduces the effective nuclear charge. As a result, effective nuclear charge experienced by the electrons is different in different orbitals. Consider another question which is based on the ionic sizes of cations and anions. The question is that a few ions are given and we have to arrange these ions in the increasing order of their radii or their sizes. The ions given are beryllium 2 positive, chloride, sulfide, Na positive, Mg2 positive, and bromide. Okay. So this is a question based on the sizes of different ions, cations as well as anions. Now firstly we will have to consider the position of these elements in the periodic table. So if we observe the periodic table carefully, we can see what is the position of beryllium. It is present in the second group in the alkaline earth metals. Next element is chlorine. Now this chlorine is present among the halogens in group 17. Next element is sulfur. This sulfur is present just previous to chlorine in the group 16. Next element is sodium. Sodium is present in alkali metals in group number 1. Next element is magnesium, which is present in alkaline earth metals just below beryllium. And last element bromine, which is present below chlorine in the halogen group, that is group 17. So now if we see, there is a cluster of these three elements on left hand side, there is a cluster of these three elements on right hand side. Now there are two concepts here. First concept is, if we observe these three ions, they are present as anions, and we know that anions are larger in size as compared to cations. On the other hand, these three are cationic species, Be2 positive, Na positive, and Mg2 positive, and we know that cations are smaller in size. So we will first compare these three among themselves and these three among themselves based on the property that we know from left to right the atomic radius gradually goes on decreasing, whereas from top to bottom down the group the atomic radius goes on increasing due to addition of extra shells. Okay, now let us compare these three elements first: sodium, beryllium, and magnesium. Now when we move from beryllium to magnesium, the atomic radius goes on increasing. So if we have Be2 positive and Mg2 positive, the size of Mg2 positive will be larger and beryllium will be smaller. When we compare Na and Mg, when we move from left to right, the ionic radius or atomic radius decreases. In other words, we can say that Na positive is larger in size as compared to Mg2 positive, which is larger than Be2 positive. So the order of these three elements is Be2 positive is smaller than Mg2 positive, which is smaller than Na positive. So this is the order of these three elements. Similarly, now we will compare these three elements. Now we know that from left to right, the ionic radius goes on decreasing, but we have sulfide which is having two negative charges. So two extra electrons are there, whereas in chloride and bromide there is one extra electron. When we move from chloride to bromide, definitely the ionic radius will go on increasing because we are moving down the group. But when we are moving from Cl negative to S2 negative, now it is not S negative only, but it is S2 negative. From right to left, the ionic radius or atomic radius will increase, and also due to presence of two electrons in sulfide ions, two extra electrons, the ionic radius will be further increased. As a result, the trend will be chloride will have smaller size as compared to sulfide, and sulfide will be smaller as compared to bromide because bromine is having one extra shell as compared to chlorine. So this is the trend of these three elements. And when we compare the cations with anions, we know that anions are larger in size, and hence the overall order becomes Be2 positive smaller than Mg2 positive, smaller than Na positive, smaller than chloride, smaller than sulfide, smaller than bromide. So this is the order of the ionic radii of cations and anions taken together. Okay, now how will you explain first ionization enthalpies of group 13 elements as shown below? Now we know that in group 13 we have boron, aluminium, gallium, indium and thallium, and the ionization enthalpy values are given as 801, reducing to 577, increasing to 579, again decreasing to 558, and again increasing in thallium to 589. Now if we see the position of these elements in the periodic table, they are present in group 13 as boron, aluminium, gallium, indium and thallium. And what is expected when we move down the group, the ionization enthalpies should go on continuously decreasing. But what we are observing, there is a decrease from boron to aluminium from 801 to 577, but from aluminium to gallium there is an increase in ionization enthalpy. Now what can be the reason for this? Let us try to understand the difference of moving from boron to aluminium and from aluminium to gallium. The atomic number of boron is 5 and that of aluminium is 13. So there is an increase in the nuclear charge by a factor of 8. Whereas from aluminium to gallium, there is an increase in nuclear charge from 13 to 31. That is increase by a factor of 18. And as a result, the force of attraction between the nucleus and the electron or our outermost electron should definitely increase much larger as compared to the increase which is experienced or increase which is observed from boron to aluminium. So there is an increase in the electrostatic force of attraction because of larger increase in the atomic number. But at the same time, there is an increase in or substantial increase in the shielding effect, because in between boron and aluminium, the number of electrons are increased by 8, but from aluminium to gallium, the number of electrons are increased by 18. So it is expected that the shielding effect should definitely predominate. But the problem of these elements which are present in between aluminium and gallium are the d block elements from scandium to zinc. And we know that the electron which is present in the d orbitals, they are present in the diffused manner and they have got very poor shielding effect. We have discussed the shielding effect in s, p, d and f orbitals, and we have already discussed that the shielding effect is maximum if the intervening electrons are present in the s subshell, and it is minimum in f subshell. Also in d subshell, since the shape of d subshell is diffused, as a result their shielding effect is very poor. Now this shielding effect cannot compensate for the increase in the effective nuclear charge from aluminium to gallium. Hence, there is an increase in the ionization enthalpy in gallium. Now, when we move from gallium to indium, again there is an increase of 18 atomic number, that is the nuclear charge increases by 18 units, while again there are 18 electrons getting added. Now whatever is the effect of intervening electrons in gallium, the same effect is present in indium. So there is no anomaly from going from gallium to indium. Observed decrease is already there. But when we move from indium to thallium, there is an increase in the nuclear charge by 32 units from 49 to 81. Hence the nuclear force increases, and again the intervening electrons which are present are in the d and f subshell. Remember that this star indicates these 14 elements which are present in the f block group, and since in these elements the intervening electrons are present in f subshell, which is a poorly shielding subshell, or the f orbitals are further diffused, and as a result they have got very low shielding effect or shielding property, and hence what we see is from indium to thallium there is an increase in first ionization enthalpy. Hence, in short, we can summarize this as from boron to aluminium there is a rapid reduction in the ionization enthalpy. From indium to gallium there is a slight increase due to poor shielding effect of d electrons. From gallium to indium, as expected, there is a slight decrease, but from indium to thallium there is a slight increase due to very poor shielding effect caused by the f electrons. Next question is, successive ionization enthalpies of an element are as follows. So first ionization enthalpy, second ionization enthalpy, third ionization enthalpy and fourth ionization enthalpy values are given in kilojoule per mole for a particular element, and we have to identify the element among lithium, beryllium, boron, carbon and nitrogen. So which element is among them can have these values of successive ionization enthalpies? In order to explain this, we will have to write the electronic configuration of lithium, beryllium, boron, carbon and nitrogen. Now lithium electronic configuration is 1s2 2s1. Beryllium has an electronic configuration of 1s2 2s2. Boron has 1s2 2s2 2p1. Carbon 1s2 2s2 2p2 and nitrogen 1s2 2s2 2p3. Now if we observe these values carefully, there is threefold increase in the ionization enthalpy from first to second. It means that first electron is lost easily, second electron is not lost easily at all, because 3 times extra energy is required, 801 and some 2400 kilojoule. Okay, from second to third the increase is not that drastic, but third to fourth there is a very rapid increase. It means that fourth electron is not lost easily at all. It's very difficult to remove the fourth electron. Okay, so the removal of second electron is difficult and removal of fourth electron is very difficult. This can be seen from the electronic configuration. If we consider lithium, the first ionization enthalpy will be low, second ionization enthalpy will be high, but there cannot be a fourth ionization enthalpy in lithium. In case of beryllium, there will be first and second ionization enthalpy should be low, third ionization enthalpy should be very high, because the removal of electron is from 1s, which is not matching with these values. But when we come to boron, first ionization enthalpy is low, second and third ionization enthalpies are larger, which is matching with this, and the fourth ionization enthalpy is corresponding to removal of electron from 1s, which is much larger as shown over here. Hence, we can conclude that it is the boron atom whose ionization enthalpies are given over here. If we consider carbon and nitrogen, for carbon these two electrons will be lost easily and third ionization enthalpy will be exceptionally high. In case of nitrogen, the fourth ionization enthalpy will be directly high, and as a result we can conclude from all these 5 electronic configurations that this is the boron atom whose ionization enthalpies are given over here. In other words, as we have discussed the applications of ionization enthalpies in the previous classes, we can conclude which element is there on the basis of the given ionization enthalpies. Now next question is, how will you explain second ionization potentials or ionization enthalpies of chromium and copper? Now this is a graph of the ionization potentials in kilojoule per mole for atomic number 21 to 30, that is the 3D series elements from scandium, titanium, vanadium, chromium, manganese, iron, then cobalt, nickel, copper and zinc. The first ionization enthalpy continuously goes on increasing in a gradual manner as we are moving from left to right in a period. So there is no anomaly at all. But if we observe the second ionization potentials, we can see that chromium and copper have got exceptionally high second ionization potentials. Now these two values can be explained on the basis of their electronic configurations. The outer electronic configuration, or we call as a condensed electronic configuration of scandium to zinc, they are having the core shell of argon with 18 electrons, and the outer electronic configuration has 3d1 4s2, 3d2 4s2, 3d3 4s2, and the anomalous electronic configuration in chromium 3d5 4s1. After that again the 3d is successively filled with another anomaly in copper with 3d10 4s1 configuration. So chromium and copper are having anomalous electronic configuration because of the extra stable nature of half filled and completely filled D subshell. Here D5 is a half filled configuration, D10 is a completely filled configuration. If we consider the second ionization enthalpy, now the first electron definitely goes from 4s, and the second electron in all the elements except chromium and copper, they are taken out from the 4s subshell. But in case of chromium and copper, the second electron is to be taken out from 3d subshell, which is a third shell, and hence it is always difficult to remove electron from inner shell as compared to outer shell. In all the other elements, second electron is going from the fourth shell, whereas in chromium and copper, the second electron is taken out from the third shell, and hence their second ionization enthalpies are much higher as compared to the two elements which are present beside them, that is vanadium and manganese over here. Okay, so these are the two anomalies observed in the second ionization enthalpies. Now Mg2 positive and O2 negative ions are isoelectronic, and we have to compare their ionic sizes. Now we know that what is isoelectronic ions? They are having same number of electrons. Now magnesium 2 positive, magnesium atomic number is 12. Magnesium 2 positive is 10 electrons, that is isoelectronic with neon, and oxygen with 8 electrons added 2 electrons forming an oxide ion having again 10 electrons. So they are isoelectronic in nature. Now we have to compare their ionic sizes. Now we know that Mg2 positive is a cation, and so it is smaller in size as compared to the corresponding atom. The nuclear charge is more, and so the force of attraction is more. Oxide is an anion, and so it has larger size because the nuclear charge is less as compared to the number of electrons which are present, and hence force of attraction is less. So we can summarize that oxide ion is much larger as compared to Mg2 positive ion. This is another question, and which is based on the difference in electronegativity of the same element in different compounds. For example, the question is electronegativity of carbon is different in methane, ethylene and acetylene. In methane, the electronegativity is 2.48. In ethylene, it is 2.75. And in acetylene, it is 3.29. The question is, we have to explain this why. The same element showing different electronegativities in different compounds with another same element, hydrogen. Now, what is the difference between them? The difference is the difference in the hybridization of the carbon atom. What is the hybridization effect? The effect of hybridization is on the percentage S character, and we have discussed in our previous class that the electronegativity depends on the percentage S character of different atoms. The hybridizations are, in case of methane, the hybridization is sp3, and in sp3 hybridization, out of the 4 hybrid orbitals, only one is s orbital, that is the percentage S character is 25%. In case of ethylene, the hybrid orbital is sp2 and sp2 orbital has 33% S character. In case of acetylene, the hybridization is sp, and as a result, the sp hybrid orbitals have 50% S character and 50% P character. Now, since S orbital is more penetrating in nature, hence it has got higher hold of the nucleus on the S orbital as compared to P and D orbitals. In other words, with increase in the percentage S character, the hold of the nucleus on the electron pair goes on increasing. Hence, the electronegativity goes on increasing from methane to ethylene to acetylene due to increase in percentage S character. What is the effect of oxidation state on electronegativity? If you have a same element in different oxidation states, then what will be the effect on the electronegativity of that ion? We know that higher is the oxidation state, more is the positive charge on the atom. And more is the positive charge, more is the force of attraction between the nucleus and the outermost electrons. Hence, we can summarize that the electronegativity goes on increasing with increase in oxidation state. Take an example. Now, thallium existing in 2 oxidation state, 1 positive and 3 positive. The electronegativity of thallium positive is 1.62. But that of thallium 3 positive is 2.04. Similarly, stannous and stannic, Sn2 positive, Sn4 positive. Sn2 positive is having electronegativity of 1.8, whereas Sn4 positive has 1.96. Ferrous and ferric, ferrous Fe2 positive with 1.83 and ferric Fe3 positive 1.96. Cuprous and cupric, cuprous with 1.9 because it is 1 positive charge, cupric with 2 positive charges, electronegativity increasing to 2.00. This is what is the effect of oxidation state of the same element, but they have different electronegativities in different oxidation states. Why zinc, cadmium and mercury are not considered as transition elements? Now we know that the transition elements are the elements which are placed at the center of the periodic table and having properties intermediate between the S block elements which are present on extreme left hand side and the P block elements which are present on the extreme right hand side. So elements having properties between S block and P block elements, they are called as transition elements and they have partially filled d subshell. But Zinc, cadmium and mercury have outer electronic configuration of Nd10NS2. Now they have fully occupied d subshell, and since they are fully occupied d subshells, they are not classified as transition elements, even if they are considered under d block elements but not the transition element. Let us summarize the trend of all the periodic properties in the periodic table from left to right as well as from top to bottom. If we show all of these in a single diagram, we can see one by one the atomic radius goes on decreasing from left to right or goes on increasing from right to left, whereas the atomic radius goes on increasing from top to bottom. Ionization energy goes on increasing from left to right, and ionization energy goes on increasing from bottom to top. Electron affinity goes on increasing from left to right and bottom to top in the periodic table. The non-metallic character increases from left to right, while the metallic character goes on increasing from right to left. So if we summarize these properties, we can say that the atomic radius decreases in a period, increases down the group. The other properties go on increasing in the period while they go on decreasing down the group. This is all about periodic properties and various questions based on the trends in periodic properties. In the next module, we will be discussing about chemical bonding. So this is all about module number 2. This was the second module among the 4 modules in this particular course. Thank you very much.